So you remember we said that if your constraint can be written as a function of your generalized coordinates, so you have, I don't know, n of them, so maybe q1, q2, so that you have an equation, then obviously, so maybe more than one, then obviously you can get rid of some of these coordinates and reduce the problem to the actual number of generalized coordinates that, remember, they are linearly independent. They're independent. And they completely fix the status, of your system. Then what if you also have, so this was the definition of holonomic constraint. How about if you also have some of the velocities? Now this is not a holonomic system, because I said that in fact to solve this you need to know already the solution, that is the velocity in terms of the coordinates, and therefore until you have solved the problem you cannot solve this equation and you cannot reduce the number of coordinates. Okay. However, there is a class of problems that are called, I don't know, maybe semi-holonomic systems, in which the constraint comes in with velocities that can be written in this form. So assume that you can write, so you have some coefficients here. So these are numbers, okay? Ik is a matrix, okay? You know about matrices, right? I guess. And here you have differentials of your generalized coordinates, and maybe you also have the time, okay? So here you are supposed to sum over k. So you have i's of these, so i's run from 1 to, I don't know, m, I think, yeah. So you have m equations telling you something about the constraints, and they can be written in this form. If you remember, we discussed something of this when we, for instance, you remember the disk rolling without slippage. And it was that you had that theta, so this was the disk, right, with the one coordinate. It was rolling on the plane, and you have the coordinates on the plane. You remember that the RT dot was equal to x dot, right? This is the definition of a rolling disk without slippage. You see, this is exactly in this form, because just get rid of the derivative. That means that the change, the infinitesimal change in the coordinate theta is related to the infinitesimal change in the coordinate x by these obvious relations. And you see, this is a special case in which out of these m equations, you just have one. You don't have this part here, you just have this part here, right? So you see, this is just a generalization of this case. So for this class of constraints, so it's a particular class. It's not holonomic, because you see, I cannot write theta equal x or something unless I integrate. To integrate, I need to know the solution. So what can I do in this case? Well, there is a technique, and this technique is called the Lagrange, well, not surprising, the Lagrange multipliers. You see in a second why. That essentially you replace the Lagrange equations with a new set of equations in which this constraint enters, and you have more unknowns, but you have more equations, and then you solve them together, and you find the solution. How do you get this? You see that if this constraint equation is true, okay, let's do again this virtual displacement, right? The virtual displacement remember, was a delta q of k of each of your coordinates that was for fixed constraint, you move just a coordinate. So there is no delta t, and if you do this variation, clearly this part here must vanish. So you have something like d k, right? For each of these k, a I k must vanish, right? Because I'm putting here a virtual displacement. It's a virtual displacement, so there is no change in t, okay, because everything is frozen. And because of the constraint, I forgot here the 0, clearly. Because of the constraint, this part must vanish under virtual displacement. And if this vanishes, it also vanishes if I multiply by a number that, well, if I have m of these, if I multiply each of these terms, you see I have I of these, I going from 1 to m, if I multiply by a constant. This constant, lambda, is the Lagrange multipliers. So I'm introducing a new unknown that is this constant, okay? But because of this property, you see this goes into the Lagrange equations that I derive exactly by applying this virtual displacement, this virtual displacement in the equations. In other words, if I do exactly what I did before and I derive my integral from point 1 to point 2, remember that by using a Hamilton principle, and according to this variation, I was getting here, let me write it this form, dl, right, dqk minus dt dl dq dot k. This was the part that I obtained last time by using Hamilton principle just on the Lagrangian. But I add this part here that you see, add this part plus lambda, well, I have to keep the sum, right? I have a sum of all the possible, let me call L, lambda L. So the sum of all these possible terms, L, I have a K, so K. And everything, this and this, is multiplied by the dqk, okay? And the Hamilton principle tells you that actually here you have a sum, right? Because you have a sum of all these possible k, with k that goes from 1 to what? Well, actually it goes to n, right, plus m, if m is the number of this constraint. Because of this constraint, here you have n plus m generalized coordinates, right? So you have too many generalized coordinates. Some are not independent because of this constraint. But it's okay. So you have n plus m equations in n plus m unknowns. So the system should allow you to solve, okay? So you have n q coordinates and m lambdas. So you have n plus m independent variables. And you have n plus m equations. Okay? So, I mean, in other words, if I now, each of these terms, right, because these are arbitrary, so each of these terms must vanish. So in other words, now I get the new Lagrange equation that the new, that this was the old one, and this is the new one with this additional piece. So in other words, I require that each of these terms within the square brackets must vanish, right? So that means, let me write the Lagrange equation in the usual way. I take the derivative of dl dq dot k minus dl dqk. Okay, so this must vanish, so must be equal to And of course, okay, so these are k, so these are n, and where are the others? The others are the constraint. The other m equations are these here. So the set of equations that you are supposed to solve are these plus the one there. Now k, okay, well, let's call it L. Well, we can call it k, it doesn't matter. Where here you take the time derivative of this so that you have the velocity q dot k plus maybe if you also have an explicit time dependence, these I t terms. This is a constant. This is just equal to 0. Okay. So formally, in the case your constraints are not holonomic, but they are semi-holonomic, meaning that you can write the constraint in that form. Then instead of having to solve your usual Lagrange equations that were up here, you have to solve this slightly more complicated system. Okay. So if the constraints are complicated, this becomes complicated. But in general, they are simple. Let's see just two examples, so that will make it maybe clearer what you are supposed to do. For instance, let's go back to this rotating disk. Let's take the Let's take the usual plane with gravity, and put, instead of having just a mass, let's put on top of this a disk with radius r. Okay, and that is rolling down the plane here without slippage. So that, again, you have the constraint that I've written before. So as usual, first question, how many degrees of freedom? So you have a disk and on this plane. So how many degrees of freedom, how many coordinates do I need in order to completely determine the position of that rolling disk? Let's have a poll. Who says 1? No, you? Okay, 1, 2, 3. Okay, 4. So try this mental exercise that I suggested. So you give a coordinate, and then you see how much you can still move given that coordinate. So for instance, let's call the distance from here to the point at which the disk is touching the plane, let's call it x. Okay? So now I fix this. Can I still move my system and keep the x fixed? If you think yes, that means you have an additional degree of freedom, right? If you think no, then you are done. You only have 1. But clearly here there must be an additional degree of freedom, because otherwise this would be exactly the same problem as the point particle. Because the point particle, that is, you just have this ideal object that is a point particle. Actually, in this situation, it has only 1 degree of freedom, because it's bound to move along this line. And if I give x, that's it. I mean, I've told you everything, right? But here is a little more complicated, because I can still keep x fixed, but I can rotate this disk. I don't know the exact position of this rolling disk. So clearly here there must be some angle, theta, I guess I call it, theta, that tells me the position of the rotating disk, so 2, okay? So now actually it's completely fixed, because I tell you it's down here, then there is a mark somewhere on this disk, and the angle between, say, the vertical position and this mark is given by theta, and the disk is completely fixed. In fact, as I wrote before, the fact that the disk is rolling down but not slipping, so that it tells me that the amount, the change in the x coordinate must be exactly matched by the change in the rolling down of the disk. Okay, if this rolls down a little bit, r delta theta is the amount of the rolling down, and this must match exactly the change in position on the plane. Okay, if that's not the case, you have slippage. That is these things here. So if you walk like this is true, but if you slip, then it's not true. And so this is the constraint. This is this part here. And of course, it's a very simple case in which k is just equal to 1. I don't have this. I just have two terms here. In fact, I can determine this constant that I call aik or ait. Well, this is 0 because there is no, right? And I can write this in this form here, dx minus r d theta equal to 0. That is in that form. And that tells me that ax. So now I decide to call the coordinate x and theta. So I have an ax, that is the coefficient of the x dot term, that is this, is equal to what? Actually, I wrote it the other way. It doesn't matter. So then it's minus 1, okay? And theta is equal to r, right? And how many Lagrangian multipliers do you expect to have? Why 2? For each of these equations, you have one multiplier, right? You see, here you have these coefficients. No, the sum is over, you see, the sum is here over, so you just have one. So in other words, you write this in this form here, r. This is the Lagrange multiplier. So you have as many Lagrange multipliers as equations that you write here. If you had two of these equations, you have two. So actually, the problem is that you have two coordinates that you have picked to be x and r, and one Lagrange multiplier that I call lambda. So yes? Just by this definition. So the definition here, you see, you write a, I, k, d, q, k, right, equal to 0. This is the constraint. And you have, so I here is just 1, because I only have 1, so I can get rid of this. And then the name of my coordinates are x, so this is ax, plus the other is theta, so a theta d theta equal to 0. Okay, so then I compare these two, and you see that this must be equal to minus 1, this must be equal to r.
Why didn't you consider the AIT?
Because there is no, you see, there is no, this comes from if I have something that depends explicitly on the change of time. But here there is no. You will, if you had something plus 3 dt, then this would have given you that term. But there is nothing like that. If you wish, that's usually the case. You don't have an explicit well, it is the case if your constraint depends explicitly on time. Like, say, if you put something on something that is rotating, right, so that at different instant of times you get different positions, then you have also this. But here you see there is no explicit dependence on time. I mean, the constraint is always the same, so I don't have that. Any? You remember, you see, you just have this. You take your constraints and you multiply by the Lagrangian multiplier. So in this case, it's trivial because it's just one that multiplies everything.
When we look at the definition,
Yes?
you have the coefficients AI, K are multiplying velocity.
Yes. No, but it's the same because you see, I can do this. And then I have the velocities. I wrote it here in terms of the velocities because within the context of the Lagrangian equations, you always talk about generalized coordinate, generalized velocities. But you may as well here think of a small change. Okay? Okay, so we have taken care, according to this prescription of the constraint. We still have to write the Lagrangian because that's we have two. So let's write together so the Lagrangian is the kinetic energy minus the potential. So let's write the kinetic energy of this system. So maybe you write it, or you tell me what to write. So this is the kinetic energy of a disk. Okay, so this kinetic energy must be the kinetic energy of the center of the mass of the system, right? You know this, right? If you have a rigid body, we'll come back to that, but you must know that already. The energy is the sum of the kinetic energy as if all the mass of the body was at the center of a mass, right? Like a point. Plus whatever energy is due to the rotation about that point due to the fact that it's an extended body, right? So let's write first the easy part. What is the kinetic energy? This disk, let's say, weight m. Okay, so what is the kinetic energy of the center of the mass of that disk? Right. So that takes care of the kinetic energy of the center of the mass, but you also have this rotational energy. Now this depends on things that I don't know if you know or not, but it doesn't matter. This the momentum of inertia about right, because it depends how the mass is distributed. We will come back to that later on when we discuss the. But so just take you just replace here, right, this momentum of inertia, and it just happened for a disk that is uniform. It's just half of the mass, so it just comes out like 1/4 m, and then you have to multiply by the angular velocity, right, omega square. And what is the angular velocity? It's just r theta. So here I call r the radius. So I have this. So this is the kinetic energy for this system. Do you agree, or have you heard about this momentum of inertia before on TV somewhere? No? Okay. Well, we'll come back to that briefly. So what do I need more? Well, I need the potential energy of these things, right? And I guess to write the potential energy, I have to give what this angle is. So let's call it phi. It doesn't matter. What is the potential energy for this? Let's call, if you call this height L, right? That could be a possibility. Then it is just, well, it's the mass, right, time g. And then I have to, well, maybe I start counting from here, I go down. So it's x projected on this on this component, right, the vertical component. So it's just L minus x sine of phi, right? You can always shift, as I told you many times, by a constant. So this looks convenient. So now I have the Lagrangian, right? Because the Lagrangian is just t minus v. And I have the Lagrangian, so I can plug the Lagrangian in these equations. I have two of them, because I have x and theta. Two of them, plus this. I have three unknown, the trajectory x as a function of t and theta as a function of t, and then, of course, also lambda as a function of t. Then we will discuss what this lambda is physically, but for the moment, it's just the Lagrangian multiplier that is helping me out. So let's write the Lagrangian equations. Let's start from, well, I don't know, let's start from x. Okay, so I have partial derivative of L with respect to x dot. So where is x dot? In here, it's only there. So I guess I have m x dot. But okay, we already know that we have to take the time derivative. So I may as well write the acceleration with two dots. Okay, minus. So this is the first term for the first equation. Minus the partial derivative of the Lagrangian with respect to x, okay? And x here, it's only in here. And you see that it's minus, the partial derivative is mg minus mg sine phi, but I get an extra minus because the Lagrangian is t minus phi, and then I get a minus from here. So odd numbers of minuses give minuses, right? So that in that way, you know that that if you get the wrong sign, you have done an odd number of mistakes. And so you get minus, I say mg, right, sine phi. This is just a constant, right, because phi is not, theta is our coordinate. Phi is just a number that you can plug in at the end of the problem. But wait a second, you also have this term here, right? So what should I write? You see, this thing here is minus, right? You have lambda. Yes? Ask me. It has nothing to do. Okay. So here you should put, you see, here you have x, so you have to put the coefficient lambda for the ax. The ax has a minus, right? Has a minus lambda. So if I take it on the other side, I just get plus lambda equal to 0. All right? So this is the first equation. Second equation, now I have to look at the dependence of my Lagrangian on the theta dot and theta. So where is the theta not? It's right here, right? So I can write that. It's just 1, so 2, 1/2 mr square theta. And again, I may as well look at the acceleration and write theta dot dot. Then I should look for the dependence of your Lagrangian on theta. So where do you have theta in the Lagrangian? So how is this variable called? Cyclic. So that means what we said last time, that there must be hidden somewhere some conservation. But let's not worry about that. Then I have the lambda. The lambda part now is this one, right? Is this one here. And so I have r times lambda. But now the sign is plus, right? So when I take it on the other side, I get a minus. Is this thing with the lambda clear or not? So I mean, I'm writing these equations, right? The first one I wrote was d dt dl dx dot for our case, right? Minus dl dx equal, I have to put here my coefficient, but I only have one for x of this coefficient. There is no sum here. So I only have lambda ax. The second equation is dl d theta dot minus dl d theta equal lambda, just the same coefficient, a theta, right? These two equations. Now, what is ax is minus 1. What is a theta is r. So now I take the derivatives, I write the Lagrange equations, and on the other side I have minus lambda for the x that I brought it on the other side, and I have r lambda for the other equation that I take on the other side, and I get a minus. Okay? So that's the procedure. I'm still short of one equation, right? And I said that the last equation is the constraint itself, that is this one here. I erased the 0. Okay? And now I can just take, I write it using the velocities, so that is just r theta dot equal x dot. This is the constraint. And now I can solve it because I have three equations. I have three unknowns, x, theta, and lambda, three equations. So I'm confident that I can, well, that is a well-posed problem at least. And I can try and solve it. The potential energy. Well, it's the same, really, because I can shift it by a constant. So it's, I mean, it depends how you measure it. Yeah, okay. But it's the same, because you just add the subtract mgl sine phi. Yeah, no, but you see the difference between the two is just a constant number. So I can always, so I wrote it like this, but you can write it also. So mgl, well, you want to write it like this. No, with the sine phi only here. Is that what you want to do? I think so. But it's the same. You see, I add the subtract some constant. I add the subtract, for instance, I add mgl sine phi, and I subtract mgl. Then is what I wrote. You can always add the subtract constants. So I wanted to write it in a nicer way, but okay. You see, I mean, they give rise to exactly the same equations. So if they give rise to the same equations, they are the same things. Let's try to solve these equations, okay? So this is the constraint, and these two are Lagrange equations. How do you solve these equations? Well, for instance, you can so if you take the time derivative of the constraint, now you have an equations that allow you to write, you see, you can replace this theta dot dot by using this, right? So that you get 1/2 m r square. Now, so theta dot dot is x dot dot divided by r, so 1r goes. Right? And also r I can simplify, so this gives me that 1/2 mx dot dot is equal to lambda. Please. The potential.
No?
I don't. What is written here? Ah, x sine. Yeah, that's what I have there, right? Yes.
Parce que calcul, en fait c'est 10 égale L minus I find out
No, it's the same, no?
this mg factor L moins x sinus.
But it's the same if you add the subtract the constant, right? You want this distance here, right? So, okay, this distance here is what? So, I mean, if I take x sine phi, right, this is this. So, actually, that's all I need. Then I can shift this by whatever amount I want. If you want to it depends where you start counting. Say, if you start counting from there, you only need this. Or you can subtract this, then you get this distance. So you start counting from there. It's the same, right? Because if I take the derivative of your result and mine, I get exactly the same term. It depends where you start counting. That's not it's not a defect of this. You must have this. You can use this to your advantage. You know, in some situation, if you put a 0, your potential, everything simplifies. Okay, so do we all agree on that potential now? So I've derived this that gives me lambda, the Lagrangian multiplier, as a function of the acceleration. Actually, this is kind of interesting because you see lambda is exactly, you see, sort of half. So what is mx dot dot? This is like the Newton force, right? Because this is the acceleration in the x direction of the center of the mass. So it looks like the Lagrangian multipliers that we introduce in a formal manner, it's half of the acceleration of the center of the mass in this problem. But let's finish the. So now I can, so I take lambda from here, I put it in here, and I have a single differential equation of x. So let's do that. So I have mx double dot minus mg sine phi plus lambda, that is 1/2 mx dot dot equal to 0. So I have 1 plus 1/2, that is 3.5 mx dot dot equal mg sine phi, right? As expected, the total mass simplifies because you know that in the gravitational field, all bodies fall at the same, with the same acceleration independently of their masses. And, well, okay, I can solve this. It's x. So the acceleration is given by what? 2/3 g sine phi. And actually now I can put it back there. I get that lambda is, right, I take x dot dot from here. So I get that m is mg sine phi, then 2/3 divided by 1/2, so I only have 1/3. And if you want, I can also write the equation for theta dot dot. That is just, well, just from there. 2g sine, what did I write here? This is a phi. 2g sine phi 3 divided by r, right? Because of now these are, so this is solved, and these are two very simple differential equations because you have just the acceleration is equal to this constant. So if I solve it, I know that I'm going to find the usual trajectory, 1/2 times that acceleration times square plus whatever initial velocity times t plus the initial position, right? And you see it's kind of interesting because here you can what would have been the acceleration if it had been a point particle? What would have been the acceleration? So what would have been x dot dot if instead of having a disk, I had a point particle? This you know is just g sine phi, right? It's just a component, I mean, falling down this way. So how come, you see, I have only 2/3 of that. So how come? Well, 1/3 of that has gone into the lambda. So in a way, it has gone into the constraint, okay? And in fact, that allows you to to give the interpretation of the Lagrangian multiplier, because if you reintroduce this coefficient a, right, you see that if you look ax lambda, right, that it was -1 lambda. So now you can solve this. It's minus mg sine phi divided by 3. And the other a theta lambda, that is the one in the theta direction, that is just, where is it? It's here, 1/3 mg sine phi. In a way, you see, this is a sort of the friction that you have in the system, exactly because you are not, you are rotating, so you need some component working against you in such a way that you can rotate. So instead of having g sine phi, you have only 2/3, because 1/3 of that acceleration, or if you wish, 1/3 of that force, if you multiply by the mass, has gone into friction. And the other, and then you have 1/3 that has gone into the torque, due to the fact that you are rotating. So indeed, the Lagrangian multiplier is telling you about the forces in the constraint. Okay, so it's interesting. It allows you to compute, for instance, the problem could have been, what is the friction, or the friction in this system? Compute the force of the friction in the system. And in principle, this is something that you cannot do using the Lagrangian, because usually you get rid of the constraint, so there is no way that you are going to compute forces due to the frictional forces that they come from the constraint. But for this case, for this class of systems, this is the way to do it. Okay, so that's nice. Kind of nice, I guess. Questions? So I guess we can try a slightly more complicated example in which you have more than one constraint, and then we leave at that. So let's go back to the other problem that I sort of mentioned last week. That is, again, a disk like this that is rotating without slippage, but now is on the, you remember, a disk on a plane, right? Like a disk in this room. You remember this has an additional degree of freedom because it rotates. So you have two coordinates now because we are on the plane, not on the line like there. So you need two Cartesian coordinates to fix the position of the center of the mass. But then it can also, it rotates like this, right? It can also rotate about the principal axis. So it's going to be a 4 degrees of freedom problem. So let me erase this. So as I said, let's say on a plane, we have a disk of mass m, big M, and so it's following some trajectory in this plane and is rotating. Okay, so we need what? We need x and y for the position of the, say, center of mass. Then we need an angle on the disk, let's call it phi, and then we need an angle that gives me say, for instance, the angle with respect to the x. I don't know. This angle here. No, or through the center of mass. I mean, through this point here, something like this, theta. So, x and y, then the rotational angle, and then something that tells you how this is pointing with respect to, say, the x. What are the constraints here? So again, is a constraint about the rotation of this, about the rotation of this angle, right? So it has to do with the velocity. Now the velocity is not just x dot, it's x dot and y dot, right? Because I have two coordinates because I'm on a plane. So I have x dot and y dot, and they are equal to what? Well, so this is x, and that is y. It's moving, so you have two components. So let's call r, big R, the radius of this disk. You see that you have the velocity r phi dot is the velocity of this disk, but you have two components of this velocity depending on the orientation of this disk, right? We take, say, for instance, the disk is like this and is rotating, so it has a velocity. And you see that this velocity in general is going to have one component with respect to x and one component with respect to y. So I project out these two components, say x, I call it sine of this theta, and the other one, the cosine of this. And because I picked, so let me put a minus here because, say it's pointing this way, so you see that it goes to decreasing value of y if it's moving this way. But I mean, it depends how you start. So this is the constraint. You see now you have two of them. And I can write it in this differential form as I did before. And by bringing everything on the other side, you see I have so I have the dot here. So minus r sine theta d phi equal to 0. And then I have dy plus r cosine theta d phi. So I said, now I have a system with 4 degrees of freedom. So in general, if I write, you remember this Lagrangian multiplier things, I have a system with how many? Four so A11, let's call it dx, plus A12 dy, plus A13 d phi, plus A14 d theta. Right? And actually, I have 1 and 2, so I have also A21 dx plus A22 dy plus A23 d phi plus A24 d theta equal to 0. Okay? So I'm writing explicitly these things that I call A, K, I, K, D, Q, K equal to 0, right? You remember? And I said I have lambda I. So for each of these equations, I have a lambda. So I'm going to have two Lagrangian multipliers now, one for this and one for that. And you see, you have to write as many coefficients here as changes in coordinates that you have. So we have 4. So in principle, this is the. So maybe now it's clearer what the meaning of this term that I wrote at the beginning is for this case, okay? But you see, you don't have all of these coefficients, because now you look at this, that is the general form, and then you look at your specific form here. You see many terms are not there, okay? So I can identify, so for instance, what is A, so let's write the name here, that is, what is A11? 1, 1, yes, right, this. So you look, and it's there. Good. What is A12? Yes, 0. You all agree? You see, there is no dy in the first equation. So it must be 0. What about A13? That is here, because this is the, so I have that. So A13 is equal to minus. How about A14? It's not there, so I put it here. That is the list of the zeros. Okay, so I'm done with the first line. How about the second equation? So what is A21? A21, 0. How about A22? Yes. How about A23? And A24, 0. So this way you have fixed those coefficients that are going to enter your Lagrangian, Lagrange equations. So this I can remove it. Now we need the kinetic energy. Well, the good news is that, is there a potential energy here? No, because in a way you are at the ground state of this system, right? Because even if there is gravity, there is no way you can go further than this floor, and so there is no potential. So you only need to write the kinetic energy of this disk. Now, this is the kinetic energy. So let's, again, as before, is given by the energy in the center of a mass. Well, that by now should be, what is this? Yes. It's just it is. I hope by now you start appreciating how simple it is to do things using the Lagrangian, because you see, you don't have to worry. Just you write the kinetic energy, and there it is. Of course, there is also some energy, some kinetic energy in the rotation of this disk, and you have two kinds of energy, because it can rotate this way, right? But it can also rotate about the other axis. So let's not. So the moment I said the energy for a disk or for a body like this, about a given axis is given by 1/2 this momentum of inertia that we take it as a black box for the moment, times the angular velocity square, right? So let's just write it like this. Let's call I1 the kinetic the momentum of inertia about the phi, okay, the one in this direction. So this is the momentum of inertia through about an axis going through the center of the disk. So this is this. And so here I put phi dot square plus the kinetic energy in the other direction, this one here, right? If it move in this way, that I call I2. And this is proportionally to the theta dot square, the velocity, the angular velocity in the other direction. So this is the kinetic energy, very simple. And I can write the Lagrangian equations. So what are the Lagrange? So I have d dt dl. Let's just do it qj dot minus dl dqj. And I only have to remember that I have to sum here the lambda ij. Okay. So this is the usual part, this is the new part. And these I know because we just determined them. Many are zeros. I have just 4 of them that are different from 0. So I have to be careful here. And as I said, because I had 2 constraints, I have 2 of these lambdas. Okay, so let's call it lambda 1 and lambda 2. So I goes from 1 to 2. So let's write the first one. I also, I'm sorry, I have 4 Lagrange equations because I have 4 degrees of freedom. So let's start from the first one. Let's start from x. So what is dl dx dot? It's only there, right? So it's very simple. Is mx dot. I have to take the total derivative, so it becomes a dot dot. But I also have this part here, so now I have to look. I put qj equal to x, right? So for us, x was the 1. So I'm looking to what I have here. The whatever it has j equal to 1. So how many terms do I have? No, it's the second index that is not the second index. So I have to look for a second index that is equal to 1. So it's just, so here so lambda 1, A11. This is the only term, right? So A11 is 1, so I have lambda 1. Similarly, if I look now to the y component, I take the derivative, I get the acceleration in that direction, and I have to look to components that have a 2, right? And so 2 as a second index, and I only have this, it is 1, and that gets lambda 2, all right? I have 2 more equations coming from the derivatives with respect to the phi dot and the theta dot, okay? So when I take this one, I get phi dot dot from here, all right? These are all, as you notice, all these coordinates are cyclic, right? Because you see, they are only velocities because there is no potential. That's usually the case. You simply have what kind of conservation laws do you expect from that? The fact that it does not depend on x, you remember? I expect to have conservation of the momentum in the x direction as well as in the y direction, and also conservation of the angular momentum about the both axes. And that, of course, must be true. There are no external forces. The system is completely all quantities, all momenta and angular momenta are conserved. Is the energy conserved in this system? What should I look for? Yeah, so is there any? Is conserved. So always like this. So this takes care of the Lagrange equation for this coordinate, but I have to look at the part with the Lagrangian multipliers. And you see now phi is my coordinate number 3, right? So I do have two terms with that. So I have to put minus lambda 1 r sine theta plus lambda 2 r sine theta. One was a cosine, really, no? I think this was a cosine. Otherwise, they are just the same. And finally, I have my fourth coordinate. I take the Lagrange equations part. I get, as before, only I2 theta dot dot equal to what? Now I have to look to coefficients with the fourth coordinate, and those are here, but they are just vanishing, so I don't have anything. And these are my equations of motion. Okay, so it's not too, one can integrate those and find the trajectories, but let's not do that. You can do it by yourself. Questions? So that's a technique. I'll give you maybe a couple of homeworks on this. I mean, it's useful up to a point, but it's a useful trick to know. So we'll do some exercises. Or maybe not, let's see. Can I raise? Okay, so in the remaining time, let me introduce the next subject. As I said, is now we want to move on. We have learned about the Lagrangian, about all these conservation laws that we can study by this formalism. So I guess now you are eager to tackle a real problem, and I mean, the best problem is the motion of planets. That's actually where mechanics started from, right? People looked at the stars. Well, the nearest star, as you know, is the sun, and you realize that the suns move in the sky, right, every day. It's a very irregular motion, and that's what caught the attention of people, because things that are regular are simple, and it's always a very good idea to study simple systems, because usually those are the systems that tell you most. I mean, I know that the most interesting things are complicated, but unfortunately, complicated things very rarely teach you something deep, right? So the strategy, if you look at the history of science, has always been to not to concentrate on complicated systems, but to very simple systems. In all fields, I mean, if you are in biology, you don't study horses or elephants, you study bacteria, right? Or viruses. You study the simplest system, and there you understand, right? Like DNA was understood in bacteria. It was not understood on ourselves or cats or dogs, because, right? And in physics, it's the same. You shouldn't look at very complicated systems. You should start with very simple systems. And you know, what is simple and what is complicated depends on your tools. At the beginning, they didn't have microscopes, they didn't have telescopes, they didn't have accelerators, they only had their eyes and hands. And so if you look around, The only simple things are, in fact, the stars, the sun, and maybe the planets. We will come back to the planets because that's not so simple. Okay? So I suggest yourself in your life always look for simple problems and then study them very deeply, right? And you will discover very interesting mathematics, and that mathematics will carry you through understanding more complicated systems. Okay. Unfortunately, people always, you are very often they are more interested in complicated systems because they think they are more interesting, right? Because they are complicated, many parts. But then you spend your life looking at this. It's very interesting, but you don't you don't learn anything because it's just very interesting, but you don't understand anything because one time something changes, then something else. So always look for simple things. For instance, in high energy physics, right? Why we build these very big accelerators, you know that, because we look for the simplest systems that we can imagine that are quarks, leptons, and these things. Those are very simple. But they are not very interesting, right? Because an electron is identical to any other electrons, so it's not. It only has mass and charge, so it's not a very interesting system. But by studying this very simple system, we discover very profound laws that then apply to everything. Okay, so that's my message. So okay, enough about this. And back to the beginning of classical mechanics, people looked for simple systems, and the very simple system is simple, is always the same, so look at the sun. And you notice immediately that it's true that it's very simple, but it's not trivial, because, for instance, the sun, it's true that every morning rises and then sets, but not at the same time, at least here. I don't know, maybe well, it depends where you grew up, because if you are at the equator, then it's always at the same time, right? But here you must have noticed that it's very different. For instance, now it's almost dark, while when you first came here, you know, up to 9 o'clock or something, it was, so it's not true that it's always the same. And also, if you have noticed here in the Gulf of Trieste, it doesn't set always in the same place. When you first arrive here, it's set very, well, in that direction, roughly. And now it's slowly moving in this direction. So not only the time at which the sun rises, well, here it's difficult to see the sunrise, but the sunset, and also the position of these changes. So it's a very regular motion of these big things that you call the sun, but it's not, you know, trivial. It's not always the same. So you have to understand why it's behaving this way. And that's what we want to do. So to understand that, you have to idealize a little bit, right? You have, and the way you idealize this system is that you take our planet and the sun, and you assume that that's all there is in the universe, right? That's actually a pretty good approximation, because everything else has an effect on this system, but is a very small effect. It's just what we call a perturbation. That's another very useful idea, that you focus on what is the most important parts of your system, and then all the rest you consider as a perturbation. Okay? So you have two bodies, and they interact through a force, I assume. That people assume, right? Because it's always there. Otherwise, tomorrow we won't see the sun. And okay, it's a central force, because it looks like it only depends on the distance. And you know that this force is Newton's law of how it's called, the universal gravitational force. But they didn't know at the time. I mean, first they discover how these things move, and then by knowing how these things move, they discover what kind of force was there. Is that clear? I mean, it's not that they knew about Newton's law. It's not called Newton's law. The gravitational law, how is it called? I mean, this F equal G Newton M1, M2. The Newton's, no, it's not Kepler. The universal gravitation or something. Okay, but this is what I mean. They didn't know that. In fact, we are going to discover this. We want to study the kinematics of the system, okay? So the only thing they knew was what they saw. So starting from the sun, they measure at what time it was rising, and what was setting, and where it was, and all the time. You know, maybe let's finish this little historical, that the next thing you can look for is at night the stars, right? And if you look at the stars, they behave very much like the sun, right? If you look at the, you know that they have names. I mean, these groups of stars, they gave names to them so that they could be recognized. And if you look over a night to the, I don't know, the Big Dipper, for instance, it moves, right? Exactly like the sun, it rises and then it sets. Some never set, like the polar star, and of course there is a reason that it never set there. But anyway, the motion of the stars is very similar to the sun, right? In fact, it's essentially the same. You have something, if you think of these stars as light, as a whole, these things rotate, right? You agree? But not all. There are stars that don't move in this way. If you look carefully, some stars don't move in this way. They move in a very strange way. I mean, they set and start, but they move in time with very strange trajectories, and that's why they were called planets. Okay? If you follow Venus, for instance, over many days, it will move against the fixed stars in a very strange way. It will move essentially like this. If you start, you know, I don't know, you start one day, and Venus is here, and here are all the other stars, okay? And they move like this. But the day after, it will be here, and then it will be here, and it will be here. It will move against these fixed stars. That's why they're called fixed stars, why Venus is not a fixed star. But the weird thing is that it doesn't simply move like this. At a certain point, it stops, goes back, and then it starts again. That's why they call it a planet, and they were really shocked. And you understand why you are shocked, because the sun, I can describe it very well as, say, the sun is on a sphere, and the sphere moves about the Earth. That explains essentially what I see, right? And the stars, by the same token, they are just holes on these spheres, right? And there is light on the other side, and what I see is this sphere rotating. I guess this is what I would have guessed, too. But the planets, they don't move in this way. You see, they move first, they go one way, then come back, then they start again. This is very hard to explain. So you need a more sophisticated theory, and that's what we are going to develop. That's what they did. They measure with a high precision, the position of stars and planets at different times during the year, and then they try to explain these trajectories. And that took a lot of time, a lot of observations, and well, we'll come back to this. So, but let's start from the first problem that I want to, so let me do that, and then we stop. So let's just start from the ideal, simplest problem, that I have just two bodies that I call the sun and our planet. And I want to describe the motion of these two. Let's not assume anything. There is a force, and I only assume that the force between these two bodies is central. By central, I mean a force that only depends on the relative distance of these two bodies, okay? So it does not depend on the velocity, it does not depend on anything else, it just depends how far this body is from the other one. This is, for us, from now on, is what we mean by a central force, okay? So how many degrees of freedom I have here? This we already counted the first day, so I have essentially two bodies, but let me assume that I can idealize the sun and our planet as a point with a given mass. Okay, so this is the mass of the sun. this is the mass of the Earth. But in fact, this is true to a good approximation, that I can always assume the Sun as a point with the mass of the total Sun. Okay, this comes from the fact that the gravitational force goes like 1 over r square. But okay, and so there are 2 points. So how many degrees of freedom? In principle, I have 6, right? Because I have 3 times 2, that is 6. So I have 6 degrees of freedom. Okay, that's what it is. But you probably remember from, well, okay, let's now I want to describe this system, so I have to introduce 6 degrees of freedom. I have 6 degrees of freedom. I need 6 coordinates, and usually this is done by introducing 2 vectors. Let me call big R the first vector that goes to say to the center of the mass of this system, right? This is what is usually done, and then I give other I give 2 other vectors that I call R1 prime and R2 prime that point from the center of the mass to the position of my 2 bodies, right? This is it's a possible so you may wonder, now I have 3 vectors, so I'm a little bit I have too many things, but the truth is that I mean this right, this R1, R2 really they are. I mean their sum is the total distance between the 2, right? So if you wish, I have a constraint, and really R, that is I call little r now, the distance between these 2 is just, well, I put this point in this way, so it's just a difference in this, because they are pointing away, okay? So really, I have 6, because I only 2 vectors. I have the vectors that points to the center of the mass of my system, and the vectors that tells me the distance between the 2 points, right? And then just to make the picture nicer, I introduce these 2 vectors, the difference of which is the total distance between the 2. Okay, so I can write the kinetic energy of this system, and as you said, well, no, as I said, is the total mass. So the Sun plus the Earth are the big one dot. So that's the kinetic energy of the center of the mass. Then I have the kinetic energy with respect to that point, and that's why I wrote it with these 2 vectors, because now I can easily write it just as R. So I guess that's the Sun. So R1 prime dot square plus 1/2 m Earth prime, well, there are too many square. Now, by definition of a center of a mass, you know that if I take m, so let me call this m1 because otherwise it's too long. m1 r, so the Sun has mass m1, the Earth m2. So m1 r prime 1 plus m2 r 2 prime is equal to 0, right? And at the same time, I have R2 minus R1 is equal to R. So this way, I can go to my generalized coordinates, if you wish, that I said are R, big R, and little r, right? Because if you solve this system, I give you the answer so that This is minus m2, m1 plus m2 r, and r2 prime, the distance of the Earth from the center of the mass, is m1 plus m2. Roughly, where is the center of the mass of the system, Sun, Earth? Roughly. It's close to us, close to the Sun. It's somewhere inside the Sun, I think, even, because the Sun is very fat and we are small. So this point is very close to here, really. I mean, but okay. So in other words, R1 prime is much shorter than R2 prime. Okay, so now I want to switch. So now I guess this is M2. No, this is M1. This is M2. This is M1, M2. That is simpler to write. So now I can write the kinetic energy in terms of my coordinates that are the center of the mass coordinate and the distance, the relative distance of from the relative distance from the Sun to our planet. And if I do that, well, the first term remains just the same. But if you plug in these numbers, you get here 1/2 m1, m2, m1 plus m2 r dot square. Right? Well, you do it if you don't believe it. You take that, plug it in, there are simplification, and the net result. Now this is the kinetic energy, okay? And this is okay. And as I said, I'm thinking that the force is a central force. That means the potential that I have to write before I can write the Lagrangian is going to depend only, so it's a function, I don't know, but it's a function only of the little r, by definition, of a central force. So by extension, the central potential. It does not depend on big R. It depends only on the relative distance, okay? Like Newton's gravitational force. And there is another nice feature because you see, now the Lagrangian is this minus this, and again, I ask myself and I ask you, is there an explicit dependence on big R? No. So big R is a cyclic variable, and that you already knew in a way, because you know that this system is going to move somehow in a complicated manner the motion between the two masses, but the center of the mass, we already discussed this, is going to stay where it is. It's a cyclic variable. That means the momentum conjugated to that variable is conserved, right? So the center of the mass of the system Sun, Earth, not only is inside the Sun, but it just stays there no matter the way we move. Okay, it's completely conserved. It stayed there. It was put there 1 gazillions of years ago, and it's still there, right? And meanwhile, we move around many, many times. Okay, so the Lagrangian here is already telling you that this part of the problem, in a way, factorizes out, because this you can solve. It's a trivial. The solution is that there is no acceleration for this coordinate, so the coordinate just stays. If it was moving with a certain speed, it keeps on moving with that speed. If it was at rest, it will just stay at rest. In fact, it doesn't matter because of Galilean invariance. For us, it doesn't matter. If something moves with constant speed or is at rest, it's just a matter of frame of references. You're familiar with that. If you are on a train, you know, I mean, if you are at the railway station, the other people are at rest. As you board the train, you start, they start suddenly moving in the opposite direction. Nothing has changed. The physics is always the same. It's just a matter of frame of reference. And here's the same. The other interesting thing, you see, it depends only on this combination of the masses, that very usually is written, this is called mu, and it's called the reduced mass. And usually it's defined like this, 1 over mu. If you have two masses, m1, m2, the reduced mass, I mean, the inverse of the reduced mass is the sum of the inverses of the two masses. You see, this is exactly what mu is. And for all practical purposes, then you see this was a two-body problem, right? Because there were two bodies. But my equations are telling me that really this is completely equivalent to a one-body problem, because you see, now this I forget about. My Lagrangian then is just 1/2 mu, the reduced mass, r dot square minus u of r, right? But this is the Lagrangian that I would have written if I had asked you to write the Lagrangian for a single body, a one body, of mass mu in a potential given by this. So you see, it's always true that the two-body problem for central forces can be reduced to a one-body problem for a reduced mass. This is very powerful because two-body problems, as you understand, it's more complicated. It has 6 degrees of freedom. I mean, you don't really want to. But one-body problem is what we have done up to now, so we will keep doing the same thing. We will solve this problem, and only at the end of the day, we will say, but this was really the motion of two bodies about interacting with the central force, but the solution will be the same, you understand, right? And this is very important, and then I stop, because even if, so this problem we will solve exactly, okay? So we can claim that we can know how to solve the two-body problem exactly through this auxiliary problem that is defined by the one-body problem. The three-body problems that you may wonder, I mean, the next level would be, okay, now I study the system Sun, Earth, and Moon. This is a three-body problem. Okay, already this problem has no exact solution. You can study this problem, but only through perturbation theory, as I said. Okay, and four bodies, you're not even allowed to talk about it. But so you see, this is crucial that you can reduce this to a one-body problem, and then this, you see, it has only 3 degrees of freedom, and actually even less because of conservation laws, as you will see. And so it's a problem that really boils down to a problem with just one generalized coordinate. Well, actually two generalized coordinates, and that is a problem that we know how to solve exactly for a certain kind of potential, not for all kind of potential. But of course we know how to solve it exactly for one important example of potential, that is the potential 1 over r, that you understand is the one that yields at the end the Newton gravitational force, okay? That we will do next week.